So in the previous lecture, I talked to you about linear solvers. And in particular, you will remember my last statement, namely that every iterative linear solver that we might use is a bad one if we don't have a good preconditioner. So the next lecture then will be how to choose the preconditioner. And when I wrote this lecture, I initially had envisioned, well, I have one lecture on linear solvers, I should have one lecture on preconditioners. It turned out that I had more material. So there will actually be 4 lectures now on preconditioners, because the preconditioner really is the central piece of the linear solver. So what you will find if you implement real problems that go beyond the standard problems, that the preconditioner will be the part of your program that you have to think the longest about. Maybe not necessarily that you have to spend the most time implementing, because there are very good libraries that implement many of these preconditioners. But certainly it is the part that is, let's say, crucial for the performance of a code, that you get the preconditioner right. And so I decided that I'd give you a little bit of an overview how you actually think about preconditioners. What are the options? What is a little bit the historical development, why we use today what we use. So this is the first lecture on preconditioners. It gives you a little bit of an introduction what a preconditioner actually is, and then I'm going to talk to you about simple preconditioners for simple problems. All right, so the finite element method gives you a linear system ax equals b, one way or another. So if you have a linear partial differential equation, then you have to solve a linear system. If you have a time-dependent problem, then you reduce it to a sequence of linear systems at every time step. If you have a nonlinear problem, then you linearize it, and for example, you apply Newton's method, and in every step of this Newton method, you would have to solve a linear system. So one way or another, you always come out with a linear system, let's say ax equals b, that you have to solve. Now, if you applied a sparse direct solver to this problem, I think I talked to you about this in the previous lecture. Essentially, you can think of this as Gaussian elimination on a sparse matrix. Then the number of operations that you have to do, that's what determines the speed of the solution, essentially only depends on the sparsity pattern, right? So we know, for example, if the matrix was dense, then you would have to do something like 1/3 or 2/3 n-cubed operations to get the matrix inverted. Or that you don't actually need to invert the matrix. All you need to do is, of course, to solve the linear system. For iterative solvers, it is not just the sparsity pattern that determines the speed of solution, but it is actually also the values in A. So the sparse direct solver does not really care what you multiply with or what you divide by. So the direct solvers only need to know where is there an entry that I need to multiply with in the sparsity pattern, and then they do it. Whereas for iterative solvers, what you will find is that, of course, you need to multiply with this matrix, and if this matrix is denser, then you need to do more operations. But the number of iterations, if the matrix is denser, you need to do more operations per iteration, but the number of iterations that you need to do depends crucially on what is actually in this matrix. And so I would like to walk you through a few of these considerations, what affects the performance of iterative solvers. Before I do this, I would like to say that we measure the performance of iterative solvers based on 2 considerations, namely, how many iterations do I need to do, and how much does every iteration cost? These are the 2 things that if I multiply them together, then that is the total number of operations I have to do, and that's roughly proportional, of course, to the amount of time that I need to spend before I get the solution x of my linear system. Okay, so what are the factors that affect the performance of iterative solvers? So certainly it is, let's say, structural properties of this matrix. For example, is it symmetric? Is it positive definite? These are things that affect which iterative solver I can use. So for example, if my matrix is symmetric and positive definite, we abbreviate that with SPD, symmetric and positive definite, then for example, I can use the CG method. And the CG method in every iteration is a lot cheaper than, for example, the GMRES method, which we need to use if I have, let's say, an indefinite non-symmetric system. But then, let's say, even if I restrict my attention only to something like the CG method, the number of iterations that I have to do depends on something, for example, like the condition number. So the condition number of a matrix, in the simplest case, I can define this as the largest eigenvalue over the smallest eigenvalue. So the identity matrix, for example, has condition number 1, and we know that the Laplace matrix, for example, has condition number proportional to h to the minus 2. We looked at this when we looked at time-dependent problems and the time step restriction. Then, in reality, if you analyze this a little bit more closely, you will find that methods like the CG method, for example, depend not only on where the eigenvalues are, but also how they are clustered. If you have, for example, a few very small eigenvalues and then a lot of nothing, and then a few very large eigenvalues, then that might be a problem that is easier or more complicated to solve than if you had the eigenvalues spread out uniformly. So, in reality, where these eigenvalues are does make a difference. The last point to mention is, so if a matrix happens to be reducible, that means that not every degree of freedom is coupled to every other degree of freedom. Then the solution of using any of these iterative methods is essentially determined by how long it would take to solve each one of these reduced factors. So I'm going to show this to you for a diagonal matrix. A diagonal matrix is the prototypical example of a reducible matrix because every degree of freedom just lives by itself. It is not coupled to any of the other entries. So a coupling would be if there's, let's say, in row 3, there's of course the diagonal entry. But then, let's say, if there are other entries in columns 1, 5, and 7, then degree of freedom 3 would also be coupled to degrees of freedom 1, 5, and 7. That means that these are coupled to each other. If entries 1, 5, and 7 are again coupled to others, I can follow this chain of dependency, and I'm going to call a matrix irreducible if every degree of freedom through this chain of dependencies is coupled to every other one. So if I have a reducible matrix, then essentially I should just look at the reduced factors individually. Of course, in the finite element method, if you have a connected domain, a domain where I can't separate it into two parts, for example, then I always get an irreducible matrix. Every degree of freedom is coupled to every other one. So I will not consider reducible matrix in the future. So let me give you a couple examples of the performance of the CG method. So if I have a symmetric and positive definite matrix A, and I can apply the CG method to it, then I can show, theoretically, that the residual in every iteration is reduced by a factor r that is less than 1. And this factor r is the square root of the condition number of this matrix minus 1 divided by the square root of the condition number plus 1. So in order to reach a tolerance epsilon, I can ask the question, how many iterations do I need? Well, I need r to the n iterations instead, where n is so that r to the n equals epsilon. So if I solve this for n, then I find that the number of iterations n is log epsilon divided by log r. For the Laplace matrix, I also know that the condition number is proportional to h to the minus 2. And so I can plug this h to the minus 2 into this factor r here, and I will find that the reduction factor is c minus h divided by c plus h for some constant c, which is still less than 1, but you see immediately that if h becomes smaller and smaller and smaller, this reduction factor actually comes closer and closer and closer to 1. And that means that the CG method converges slower and slower if I make the mesh finer and finer. So the number of steps that I need is something like this. It is on the order of log epsilon divided by h. And so you see that if I make the mesh finer by a factor of 2, in reality that means that I have to do twice as many CG iterations. Historically, this has led to the following problem. So the CG method was developed by Hestenes and Stiefel in 1952, and it is certainly one of the heroic moments in numerical analysis, one of the breakthrough ideas, that you can develop iterative methods that can solve linear systems in a fixed number of iterations. So the analysis that I showed you here does not actually reveal one of the key properties of the CG method, namely, this might suggest that we have a linear reduction in the residual, and that you can make it as small as you want if you just take enough iterations. You can show for the CG method that it actually converges in exactly n. So let's say if you have an n by n linear system, the CG method actually converges in exactly n steps. After n steps, the residual is 0. You have found the exact solution. And that is very different, of course, from things like a Jacobi iteration or an SOR iteration. So in the beginning, when people realized this in the mid-50s, there was a lot of excitement about this method, because people thought, well, this is very cool. I mean, it has the same kind of complexity as let's say Gauss elimination, because if I have an n by n matrix and I need only n iterations, I need n cubed operations in total to solve a linear system. That is the same complexity class as Gauss elimination. But then people realized that in practice, it's not that easy, because if you make your linear system larger and larger because your discretization becomes finer and finer, then that doesn't work so well. So for quite a while, the CG method actually fell a little bit out of favor, and people went back to things like Gaussian elimination, or let's say more modern versions of this, like LU decomposition, until they realized that you can accelerate this whole thing with preconditioners. And I would say that happened maybe in the 80s, very certainly in the 90s, that people started to use iterative methods for practically everything, because we started to realize how we can make this competitive. So let me show you a second example of how the CG method would perform, or actually any decent linear iterative solver. So if this matrix had the particular form that it's diagonal, then it will converge. Every decent iterative solver will converge in exactly one iteration. And that, of course, makes sense, because solving linear systems with diagonal matrices is really not that difficult. Every iteration should converge, or every solver should converge in one iteration. This is notwithstanding the fact that the condition number of these matrices, of course, might be very large, right? If, for example, A11 is 10 to the minus 9 and A33 is 10 to the 9, then the condition number of this matrix would be 10 to the 18, because the eigenvalues of a matrix like this are exactly the diagonal values. But what I hinted at before is, in this case, I mean, this is a totally reducible matrix. Every one of these diagonal blocks, of these 1 by 1 blocks, is its own reduced matrix, and each one of these reduced blocks has condition number 1. And as a consequence, I can look at the previous slide again. If the condition number is 1 of a block or of a matrix, then the square root is 1 minus 1 is 0. The reduction factor is 0, and indeed, I'm done in exactly one iteration. So the consequence of this is that diagonal matrices are particularly simple to invert with iterative solvers, and in particular that is true if the matrix A that I have is the identity matrix. The identity matrix just happens to be one particular case of a diagonal matrix. So this leads to the following idea. So if I think about something like this, I want to solve a linear system AX equals B, and I've learned that it becomes particularly simple if this matrix A were diagonal. Then maybe I should do the following. So I should find myself a matrix that I'm going to call P to the minus 1 that I need to be invertible. And I'm going to multiply this from the left to this matrix here, or A. Actually, I'm going to multiply from the left to both sides of the linear system. Okay. Now, if P to the minus 1A were a diagonal matrix, for example, the identity matrix, but it doesn't really have to be. It can be a multiple of the identity matrix, or it can be any kind of diagonal matrix. Then solving this whole linear system here would be particularly simple. right? I would be done in one iteration if it really leads to a diagonal matrix. If it is close to if the product of p to the minus 1 and a is close to a diagonal matrix, then I should hopefully be done in fewer iterations. And so this is sort of the idea of preconditioners. So precondition means I'm going to multiply this matrix, this linear system, to make it better conditioned. And that make it better conditioned means to make it easier to solve. Of course, the perfect preconditioner would be if I chose p to the minus 1 equals a to the minus 1. Right? You can't get it better, because then p to the minus 1 a would be just the identity matrix. That's not practical, but that's the perfect preconditioner. So I should talk very briefly about notation. I'm going to call this matrix p to the minus 1, but this is more because I want to stay consistent with the literature on this. In all reality, I don't actually need that there is a matrix P that I know, and p to the minus 1 then would be its inverse. I really think of p to the minus 1 as a matrix, or actually I only need it to be an operator. I need to be able to multiply with this object that I'm going to call p to the minus 1. So I'm given a vector, I need to multiply with p to the minus 1. I'm not thinking that I need actually the matrix entries of this, and I'm certainly not thinking that I need the matrix entries of P for this. So I think if I were to come up with the notation that we use in the literature, I wouldn't have called it p to the minus 1, but just P, because it's some kind of operator. And I think using p to the minus 1 is a little bit confusing, but be that as it may, that's what people use. People write p to the minus 1, and what they really mean is, well, some kind of operator that approximates a to the minus 1, because that's the perfect preconditioner, but they have no notion that you actually need to be able to multiply with p as well. We only ever need to multiply with p to the minus 1. Okay, so if I have this, then you can go back and think about how these iterative solvers work. So if you look at CG or GMRes or any of the other iterative solvers, what you will find is that all of these methods really only need to multiply with this matrix, right? So in CG, for example, you never really need access to the elements of this matrix A, but all you need to do is you give this thing a vector, and it multiplies it with this matrix, and then you get back a vector. How this multiplication actually happens is not important. And you've seen this in step 20, when we implemented all sorts of operators that have a vmult function. And in the vmult function, we didn't really actually multiply with individual elements of this matrix. But in reality, for example, we multiplied with one matrix, we did a linear solve, we multiplied with something else, and so on and so forth. So it is fully sufficient if for the linear solution, A is only an operator, and the same is true for p to the minus 1. It is fully sufficient if p to the minus 1 is just an operator. An operator means I give you a matrix and you return, I give you a vector and you return to me a vector. And how you actually do this is not important. So we don't have to think of the entries of this matrix p to the minus 1, or of p for that matter. All we need to be able to do is do matrix vector products. All right, so the third observation is that there is, of course, a trade-off. That if I were able, for example, to use p to the minus 1 equals a to the minus 1, then p to the minus 1a were the identity matrix, and I know that I can be done in one iteration. But of course, in that case, I need to spend all of the time to compute a to the minus 1. So that means that the one iteration that I do is going to be extremely expensive. So there's a trade-off that we have to strike between how many iterations do we want to do and how much does it actually cost per iteration. So for a preconditioner to be good, that means that it must be cheap to compute the preconditioner and it must be cheap to apply the preconditioner. So sometimes I need to do some work up front. I need to set up extra data structures, for example. So that would go into the computing p to the minus 1. But then I also need to apply it to individual vectors, and both of these operations should be cheap. So p to the minus 1 equals a to the minus 1 does not qualify in this regard. Actually, it doesn't qualify in both of these regards. It is very expensive, of course, to compute, but it is also not cheap to actually apply, because let's say if I had computed the inverse matrix is typically a full matrix, and so applying this preconditioner would cost me n squared operation if the matrix is n by n, right? Because I need to multiply with every element of this full matrix. I could do this a little bit cheaper if I did something like an LU decomposition, then I get it down to 1/2 of that. But ultimately, p to the minus 1 equals a to the minus 1 does not qualify as something that actually works for a preconditioner. All right, so for the next few lectures that I'm going to give you, my goal is that I give you more a quantitative analysis. I want to show you, let's say, how to think about preconditioners, what the intuition behind them is, and not so much how they, let's say, work mathematically. That when you want to analyze them, there's a lot of mathematical literature that tries to figure out how each one of these preconditioners performs in practice. And when you do this, typically what you need to do is you need to look at the spectrum of the operator, so you need to look at exactly where the eigenvalues are, and then you can prove a lot of these things. This is not my goal in these lectures. You can go to the literature and you can find this, and there are, of course, whole lectures. I could spend a whole semester talking about this, how exactly this works. My goal is more for you to have, let's say, an overview of how these things work in practice and what the ideas, what are the big ideas how we construct preconditioners. Okay, so with this, let me jump right in there, namely how to construct simple preconditioners for elliptic problems. And this is something that, like I said, was work that was essentially done from the start when the CG method was discovered in 1952 until the 1980s. On and off, the CG method was not, there was a lot of hype at the beginning, but then it fell a little bit in disfavor. But then it certainly picked up again in the 70s and 80s that people thought about preconditioners. So how do we do this, right? So we said that the best preconditioner would certainly be a to the minus 1, but we can't compute it efficiently. And if we could compute it efficiently, then we wouldn't need an iterative solver to begin with, right? So the goal of preconditioners then is to somehow approximate this. So if I can't set p to the minus 1 exactly equal to the a to the minus 1, maybe I can at least approximate it. And there are essentially two approaches to this for simple problems. Namely, we look at other iterative solution techniques, or we use an incomplete inverse. So let's say an incomplete LU decomposition of this a to the minus 1. So to look at other iterative techniques goes back to the very first iterative solvers that we had. And they date back more than 200 years to the times of Gauss, for example. So what these people did at the time is something like this. So I want to solve ax equals b, and I want to do this iteratively, so I want to form an x in iteration k plus 1 that I can compute from xk. And I'm going to do this in the following way. So I'm going to say, I'm going to use something that we call a defect correction. So the defect is axk minus b. Today we would call this the residual. And so I take this residual, I multiply it with something, and I subtract it from the previous iteration. And under certain conditions, I can show that this iteration actually converges. Now, for these Kranov space methods like CG or GMRES or BiCG STAB, I can show that Kranov space methods actually converge in n iterations exactly. So they will find the solution after n iterations, if n is the size of the matrix. These defect correction methods, they don't do that. They come closer and closer and closer to the solution, but they will never actually reach it. They will never get there, even if I could do exact arithmetic. So these are sort of, let's say, the poor neighbors of CG. But we can make them work reasonably well. Again, of course, if I could choose this p to the minus 1 equals to a to the minus 1, it's easy to verify that I'm done in one step. Because if this is a to the minus 1, then I have xk minus a to the minus 1a xk. So that is xk minus xk plus a to the minus 1b. Okay, so I get xk plus 1 equals a to the minus 1b. So in other words, whatever starting point x0 I have, x1 is already a to the minus 1b. That's the solution of the linear system. So this matrix that I have here plays the role of a preconditioner in these defect correction methods. Now let's look at some of the methods that we have. And most of these methods traditionally have used a decomposition of this matrix, or let's say a sum representation of this matrix, where I write this A as the sum of the diagonal plus the lower left part of this matrix plus the upper right part of the matrix. Okay, every matrix I can write as the sum of these three terms. So the simplest iterative method looks like this. So my preconditioner is just going to be omega times d to the minus 1, and d is the diagonal of this matrix. And again, I can show that if this omega is small enough, I can show that this method is going to converge. Now, this is an easy enough to compute preconditioner, because d to the minus 1 is something that I can compute on the fly, right? I only need to divide by the diagonal entries of this matrix. This is an O of n effort that I just divide all of these entries. And so this is something that that we know works. It doesn't converge particularly fast. As a matter of fact, it's about the worst iteration that you can think of to solve a linear system, but it works. I do want to point out one particular part. So in order for this defect correction step to converge, I need that this omega here is that I have omega less than 1 over the largest eigenvalue of this matrix. And if I only if I have this omega less than 1 over the largest eigenvalue of this matrix, does it actually converge. Now, if I think of this as this p to the minus 1 as my preconditioner, and I were to use this particular form as a preconditioner for the CG method, which is exactly what we're going to do, right? So in the CG method, I don't actually care about the scaling factor, about this omega, because I told you that in the CG method, it does not matter to me whether I end up with p to the minus 1 times a equals the identity matrix, or as a matter of fact, any multiple of the identity matrix, or any kind of diagonal matrix. So I'm quite happy to just, in the CG method, to omit this factor omega, and just come up with something where p to the minus 1a is something like a diagonal matrix. Okay, so I'm in the CG, I can forget this relaxation factor. The second best, or this, let's say the second worst defect correction method would be something like this. So I again represent my matrix A as a sum of the lower left plus the diagonal plus the upper right matrix. And then instead of just taking the diagonal here, I'm going to take L plus D to the minus 1. This is something that we call the Gauss-Seidel iteration. And out of this, I can construct the Gauss-Seidel preconditioner that, again, I can use in iterative methods like GMRES. And it's going to consist of the inverse of this thing here. And you remember that I have to multiply with the with this p to the minus 1. So what does it mean to multiply with L plus D to the minus 1? Well, if I multiply a vector r with p to the minus 1 to get a vector h, and p to the minus 1 is this thing here, then that is equivalent to solving a linear system L plus D times h equals omega times r. Well, that is easy enough to do, because L plus D is a triangular matrix. And if I need to invert a triangular matrix, essentially what I need to do is just a forward or backward substitution, right? It's all there. All right, so that is what we call the Gauss-Seidel iteration. It's easy to compute. It's cheap to compute. I can again forget about the relaxation factor. The problem that I have with this one is that the preconditioner is not symmetric. And so if I start with a preconditioner that is not symmetric, even if the matrix is symmetric, you can think of, let's say, if you take p to the minus 1 times a, if a is symmetric but p to the minus 1 is not symmetric, then you get a non-symmetric matrix. And as a consequence, I cannot use this for the CG method. I can use it for GMRes because GMRes can deal with non-symmetric matrices, but I can't use it for CG. So this is sort of a nice idea, but it's not going to work for CG. The next option that I have is that I'm going to use a method that we call SOR. SOR stands for successive over-relaxation, and it's essentially the same idea, except that instead of taking d plus L, I'm going to take d plus some scaling factor times L. And I must admit that I forgot for a moment whether it's the same omega here as here. I think it's actually not. If I were to use this as a defect correction iteration, I would need to choose different factors here. The point is that I weigh the lower triangular part of this matrix, and then the preconditioner, and again it should not be Gauss-Seidel, it should be the SOR preconditioner, would be d plus omega times L, because I can forget the factor in front here when I apply it to the CG method, for example. This is again not symmetric, but now I can make this symmetric in the following way. So there is a method that we call SSOR. The SSOR method is the symmetric successive over-relaxation, and what we do in the symmetric successive over-relaxation defect correction iteration would be something like this. So I have a factor over here, and then the preconditioner that I apply is not just d plus omega L to the minus 1, I multiply it also with d, and then I multiply with d plus omega the upper part of the matrix to the minus 1. And so the SSOR preconditioner would be this whole expression here. And if you apply this to a symmetric matrix A, so for a symmetric matrix A, U equals L transpose. And in that case, what you end up with is that this p to the minus 1 corresponds to a symmetric matrix. And that now is something that we can apply to the CG method. So SSOR is something that we use in a lot of these tutorial programs. When we precondition the CG method, then we end up with, or we use the SSOR method. A typical relaxation, a typical factor, an over-relaxation factor in SSOR, by the way, would be 1.2. So if you just choose 1, then there would be something like a symmetric Gauss-Seidel. If you choose omega greater than 1, then you end up with a successive over-relaxation method. Okay, so if you use these sort of methods, what you can show in practice is that the condition number of the preconditioned matrix is better than the condition number of the original matrix, and as a consequence, that the number of iterations that you need to do in the CG method is not something that grows like 1 over h, but for example only grows something like O over square root, O of 1 over square root of h. So for every mesh refinement that you do, you don't increase the number of iterations by a factor of 2, but you only increase it by a factor of square root of 2, for example. The exact powers that you get here are not terribly important, so you can go to step 6 in the results section. We have a little bit of a discussion about this. The point I want to make is that by using these preconditions, you end up with something that is fundamentally better than the CG method by itself. So the number of iterations does not grow like 1 over h anymore, but with a lesser power in h. But ultimately, what it ends up with is you still have a linear system where the number of iterations increases with the number of mesh refinement that you do. So you will never get to the with these preconditions. You will never get to a situation where the number of iterations that you need to take is independent of the mesh size. It will always increase with the number of cells that you have. So the finer you make the mesh, the more iterations you will need to do. And of course, for the finer you make the mesh, every iteration will also become more expensive, because when you make your mesh finer, for example by a factor of 2, in 2D the number of unknowns will become larger by a factor of 4. That means your matrix is 4 times as large, and so immediately just applying one matrix vector multiplication is going to cost you 4 times as much. So not only do you need to do 4 times as much work per iteration, but you will also need to do more iterations. So even with these preconditioners, you make the situation better, but not perfect. All right. So a common observation about preconditioners from stationary iterations, just like Jacobi or SSOR, is, well, first, they've been around for a long time. Like I said, hundreds of years. They're generally useful for relatively small problems. So relatively small means, let's say, less than 100,000 degrees of freedom. That's fine in 2D. You can solve most problems in 2D with less than 100,000 unknowns. But these preconditions are not particularly useful for larger problems. And we will have to come back to this and try to come up with better methods for large problems. Okay, so let me show you a second approach to constructing preconditioners for simple problems like this, in particular for simple elliptic problems. So if we cannot take a to the minus 1 as a preconditioner because it's too expensive to compute, maybe we can at least approximate a to the minus 1. And there is a systematic approach to this, namely even if we tried to compute a to the minus 1, we would never really do it. We would compute an LU factorization, for example. And so we try to come up with a lower diagonal matrix L and an upper diagonal matrix U, so that L times U equals A, because then a to the minus 1, to multiply a vector with a to the minus 1 would just be a forward substitution with a backward substitution with U and a forward substitution with L, right? So there are some things that we call incomplete decompositions. In particular, an incomplete LU, for example, that we call ILU. And essentially what they do is they do an LU decomposition on A, but because we know that even for sparse matrices A, the LU decomposition would be full, what we're going to do in these incomplete LU decompositions is that we only compute elements of these factors L and U that fit into the sparsity pattern of A. So we're going to throw away a lot of entries in these factors L and U in hopes that we can come up with sparse factors L and U so that L times U is still approximately equal to A. A similar method would be what we call the incomplete Cholesky decomposition. So the Cholesky decomposition would be the equivalent of an LU decomposition for a symmetric matrix A, because I can show that for a symmetric matrix A, I can find a decomposition of the form LLT. So my factor U would be just a transpose of this factor L. And the incomplete Cholesky factorization does exactly the same as the ILU, except that it's trying to find only one of these, or only one factor L, that we also want to be sparse. So these methods generally actually work reasonably well if you modify them a little bit. So there are many variants of this that strengthen the diagonal, that add a few more entries to the sparsity pattern, that have a threshold where you throw away only entries that you want to compute but that don't fit into the sparsity pattern. You throw them only away if they're small, and you keep the large elements even if they don't fit into the sparsity pattern of A, and so on and so forth. There are many variants of this, but by and large, it leads to reasonably good methods. A second idea would be that you come up with something like this. This is called sparse approximate inverse. This is a method that was developed in the late 90s and early 2000s. So you try to find a matrix P to the minus 1 that again approximates A to the minus 1. And now I have to say, what do I actually mean that it approximates a to the minus 1? And I'm going to say in the following sense. So I'm trying to find a matrix p to the minus 1 so that a times p to the minus 1 minus the identity matrix is as small as possible, right? So if p to the minus 1 were a to the minus 1, then in fact this term would be 0. So I know I can't achieve this, but I can ask for it to be as small as possible. And so if I ask for something to be as small as possible, I need to take a scalar measure of this, because I have matrices here. I need to take some kind of norm, and what I'm going to use is I'm going to take the Frobenius norm. The Frobenius norm is just the sum of squares of the elements of this matrix in there. So if I take the Frobenius norm of this sort of thing, it's relatively easy to see that this gives me a problem where I need to minimize the sum of squares of each row of where I can compute each row of p to the minus 1 separately. So this is a fairly nice problem, because if I have a large matrix, then that means, let's say 100,000 by 100,000, then that means that I can compute this p to the minus 1 by solving 100,000 independent problems. For each row of this matrix p to the minus 1, I can solve an independent problem, which is something that I can do in parallel, for example. So in this sparse approximate inverse problem, sparse approximate inverse preconditioner method, I can form this p to the minus 1. Of course, if I were to do this right, then I would end up with a full matrix p to the minus 1. Again, I can't do this. I cannot compute p to the minus 1 as a full matrix if my matrix is 100,000 by 100,000. I'm just not going to have enough memory. But also, that would mean that applying p to the minus 1 to a vector becomes very expensive. So I need to look again for sparse matrices p to the minus 1. And then that means that I want to minimize this whole expression here, not over all matrices, but only over some that are sparse, for example. So let's say I allow myself 10 or 20 or 50 entries per row, and then I will need to solve a problem where I want to minimize this least squares problem for every row, subject to the constraint that I allow only 10 or 20 or 50 entries per row. This is how these sparse approximate inverse methods work. And by and large, they work reasonably well. There was a lot of excitement about these in the late 90s and early 2000s. I think maybe we have learned that they don't work quite as well as we hoped to, but I still think it's an intriguing idea to construct preconditioners. Certainly the first really new idea in several decades. Okay, so this was how we construct preconditioners for simple problems. Let's say for the Laplace matrix, or for any other kind of matrix that is symmetric and positive definite. I should have added this. So for something like the ILU method, what you find is that computing an ILU factorization is, of course, much more expensive than let's say what you need to do up front for something like a Gauss-Seidel iteration. For a Gauss-Seidel iteration, there is nothing to compute up front. It's only that every time you need to apply the Gauss-Seidel preconditioner, you just look at, for example, the lower left part of the matrix. But you don't need to set up any data structures for this. For the ILU, you actually do have to compute something up front, namely the L and U factors, or the sparse L and U factors. And then every time you apply it, then you would have to do one forward and one backward substitution. So for these sort of methods, computing the ILU factorization is more expensive, and applying it is also more expensive. But it turns out that in practice, ILU factorizations are actually still pretty good, because you need far less iterations than you would need if you just had, let's say, a Jacobi or an SSOR preconditioner. So ILU factorizations, or the sparse approximate, lead to much better preconditioners, of course, ones that are more expensive to compute up front and more expensive to apply, but they're still worth it. All right, so let's come back to Other problems. So I talked to you about, let's say, elliptic problems, like the Laplace matrix. And so what I would like to do now is that I would like to talk about constructing simple preconditions for other problems, like, well, an advection problem. And this is something that I would say we probably figured out in the 1990s. By then, we understood what works and what doesn't work. So let me give you a little bit of an overview of other problems, or what other problems could be, other simple problems could be. So certainly that includes problems like the diffusion reaction equation. So I have a Laplace term here with a diffusion coefficient, and then I have what we call a reaction term here, because it is typically comes, for example, out of a chemical reaction. It's a source term. That leads to a symmetric and positive definite matrix here. Similarly, if you had the biharmonic equation, that's the biharmonic equation is the Laplace squared applied to a function that also, depending on the finite elements that you use, leads to a symmetric and positive definite matrix. Linear elasticity is the equation that describes how a body deforms under an external force. So your solution in that case would be a vector value quantity that for every point shows or describes what the displacement in x, y, and z directions would be. And so the linear elasticity equations in the simplest case, in the isotropic case, would be something like this, where you have two factors lambda and mu that describe the compressible and the shear stiffness of this material. And again, this sort of thing here, under certain conditions in lambda and mu, lead to symmetric and positive definite matrices. And finally, one of the things that we solved numerous times in the deal.II tutorial, so for example in step 6, would be a Laplace equation with spatially variable coefficients. So I have a coefficient a of x here that can be large and small in different parts of the domain. This too, if you integrate this by part, it's easy to see that you get a symmetric and positive definite matrix if a is bounded away from 0, for example. So for all of these sort of problems here, essentially, we end up with symmetric and positive definite matrices, and everything that I talked to you about in the previous section would apply as well. So all of the things like SSOR, ILU, sparse approximate inverse, they will all work exactly the same for these kind of problems as they work for the Laplace equation. So the slightly more interesting situation would be if you have non-symmetric problems. So for example, if you have an advection diffusion equation, so I have a diffusion term here, and then I have this transport term here. So that would be, for example, in the case where you consider the transport of pollutants in the atmosphere. Beta would be a vector field that describes, for example, the wind direction and speed at every point. You would transport the concentration of pollution with this wind field, but then there's also some diffusion of this. So that is what we call the advection diffusion equation. Of course, we could also look at the pure advection equation, the transport equation, or we could add to this equation reaction terms, and so on and so forth. So there are multiple variants of these sort of equations that all lead to non-symmetric problems. Similarly, if you take the biharmonic equation and you apply to it a particular scheme that involves not just the solution variable u, but also an auxiliary variable, then you also end up with non-symmetric problems. So for these sort of cases, the defect correction based preconditioners that we had typically continue to work. Oftentimes what you will find is that they work less and less well the further you deviate from the standard Laplace matrix. So for the Laplace matrix, they happen to work particularly well, and if you go away from this, then they become worse and worse. There's sort of an exception when you just look at the transport equation. If you manage to enumerate your degrees of freedom in such a way that you have first the degrees of freedom, let's say, on the inflow boundary, and then you enumerate all the ones that are downstream, and then you enumerate all of the ones that are downstream from these, and so on and so forth. If you manage to do it this way, then you end up with a matrix that is diagonal. That is triangular, not diagonal, but it is triangular. And of course, if you apply, for example, something like Gauss-Seidel or SSOR to a triangular matrix, what you will find is that you're done in one step. So in that case, that's particularly simple. We call this a sweep preconditioner, where you first treat all of the degrees of freedom on the inflow, and then from there you go to the ones downstream and so on and so forth. Essentially what this means is I'm going to compute the concentration here based on the concentrations on the upstream direction. So in this case, if you have a purely advection problem, then that would not be very difficult to precondition. But if you add to it again diffusion, then you end up with the same situation as before, that your matrix is, well, not symmetric, but it doesn't have the structure that it is triangular, and so I cannot expect to be done in one step. So in general, but as I said, if you deviate from the Laplace matrix, it becomes more difficult. The ILU method is typically still a robust choice in for all of these matrices, and for the biharmonic equation, well, that's sort of a special case. Depending on what kind of elements, what kind of finite elements I use, I can come up with an SPD matrix, or I need to convert it into a mixed vector value problem, and then that's an entirely different issue. So to sum this up, this whole section on preconditioners for simple problems, or let's say simple preconditioners for simple problems. Ultimately, what it boils down to is you have two options, namely these defect correction-based preconditioners and something like ILU or incomplete Cholesky or the sparse approximate inverse and so on and so forth. So for small kind of problems, all of these work reasonably well. I would say ILU works better than the defect correction-based problems, but they're more expensive to compute and more awkward to set up. But for small problems, they all work reasonably well. The defect correction-based methods have one particular disadvantage. Namely, we would call this that they have a low speed of information propagation. If you think about how something like the basic Jacobi method works. So the basic Jacobi iteration, the defect correction iteration, essentially computes each element of, I should go back and show this in these slides here. So if you look at the Jacobi iteration here, then so you take your vector xk and you multiply it with a, and you subtract from it this vector b. But this is sort of the important point. So if you think about the elements, or let's say, which other elements does a particular element of xk influence when I multiply it with a? Well, A is a sparse matrix, and in the finite element method, I build it by computing local contributions on every cell. So it couples every degree of freedom only with the other degrees of freedom on this cell, as well as on neighboring cells. So every entry of this vector xk here only affects entries that are coupled to it with a. So the resulting vector a xk has entries that are influenced by a particular vector, by a particular element of xk only to the neighbors. And then I multiply it with d to the minus 1, which is a diagonal matrix which does not couple either. And I assign the result to xk plus 1. So if I have a particular poor approximation in one particular element of this vector xk, then I can only expect this to be corrected by the neighbors. And so this is, in essence, you can think of this, this iteration that we have here as something that computes an element of, or let's say, 1 degree of freedom at one particular vertex of my mesh, for example, based on the ones around it. And so in each iteration, maybe I get a little bit better, but not by very much, because I only take into account the information from the degrees of freedom around it. And that's why I need to do so many iterations in the Jacobi iteration until I finally get something that comes close to the solution, because we know that for the Laplace equation, for example, all of the degrees of freedom are coupled with all of the other ones. So in order to compute 1 degree of freedom over here, even if let's say, even if the ones over here are already correct, the best thing that can happen is that if the ones over here are already correct, that in the next Jacobi iteration, all of the ones in the next layer of cells are correct. And then all of the ones in the next layer of cells are correct, and so on and so forth. So if I have, let's say, an m by m mesh, then it takes me at the very least m iterations, to get them all correct. In practice, I need many more. But we call this the speed of information propagation. The speed of information propagation is that in the Jacobi iteration, in the basic defect correction iteration, every degree of freedom only influences the neighboring ones. And so for finer and finer and finer meshes, you can easily see that this iteration will take longer and longer and longer. And so basically all of the defect correction iterations that we have that use these old Jacobi, Gauss-Seidel, SSOR methods, they are limited by this information propagation problem in their speed of convergence. And so as a consequence, there is really not all that much that you can do about it. If you wanted to sum this up, you can use these sort of methods for relatively small problems, where maybe that is not that big of a problem. But for large problems, let's say with millions or tens of millions of unknowns, defect correction iterations simply don't work well anymore. Similarly, for very large problems, computing the LU or IC factors becomes prohibitively expensive. And so for large problems, we have to rethink this whole approach again. And for large problems, the way to go is through something that we call multigrid. In particular, there are two variants of this. There's the geometric and the algebraic multigrid method. And these avoid this problem that we have a finite speed of propagation, or that our ILU factors deteriorate as the problem becomes larger and larger. So I will come back to multigrid methods in the next lecture and show you a little bit of how they work and why they work. So I'm going to demonstrate this to you for the Laplace equation, and then in the two following lectures on preconditioners, I'm going to show you how we can combine these building blocks to form things for equations that are not the Laplace equation or not scalar. So for more complicated problems like, let's say, the Stokes equation or the Navier-Stokes equation, how you would approach these sort of problems with preconditioning, and how we can form preconditions for this from the building blocks that we've learned work well for elliptic problems, for example.